Our next lesson is on something called colligative properties. When you take a substance and dissolve it in something else, so you take a solute and you dissolve it in some solvent, the solution will have different physical properties than the solvent by itself. And some things we're going to look at that change are vapor pressure, boiling point, freezing point, and something called osmotic pressure. So for example, just looking ahead, the boiling point of an aqueous solution is different than the boiling point of water by itself. And so we're going to start off our discussion with changes to vapor pressure, as we'll see in just a minute. So it says in the notes, these are properties of solutions that are affected by the presence of solute. What's important to understand is that it is the number of solute particles that we need to look at and not the particular type of solute. There is one exception to this. We'll talk about the difference between a molecular solute and an ionic solute. But if you have two different ionic solutes, chances are the properties of their solutions, if you dissolve them, say in water, will be the same. A little different, as we'll see later on. All right, so let's take a look at Raoult's law. Some vocabulary first. A substance that readily evaporates is said to be volatile. So a lot of times we as students think that volatile means explosive. It doesn't mean explosive. It just means anything that is able to evaporate is volatile. There's different degrees of volatility. The more easily something can evaporate, the more volatile it is. And so we'll be talking about volatile and non-volatile solutes. Non-volatile, of course, then is a substance that does not readily evaporate. A substance that, like sodium chloride, for example, will not just turn into a gas, evaporation, changing from a liquid to a gas. We have the term here in the notes, vaporize. So technically this includes evaporation and sublimation, something changing into a gas. So volatile substances that can change into a gas by themselves, non-volatile substances that cannot change into a gas by themselves. So here's how it works. Solute particles interfere with solvent particles vaporizing. So if we recall to go back to evaporation, evaporation is a process where a liquid turns into a gas and only the particles at the surface are able to turn into a gas. So the particles at the surface of a liquid possess enough kinetic energy to break free of their attractive forces and turn into a gas. However, what we're saying here is that when you have solute particles dissolved, those solute particles interfere with the solvent's ability to evaporate. So less of that substance evaporates, which results in a lower vapor pressure. There's a picture in your book on page 522 at the bottom. It shows pure solvent versus a solvent with a non-volatile solute. I'll kind of try to draw a picture too, just to further show you what's going on here. So imagine you have some liquid and you have all these particles at the surface. So let's say this is water. Okay, so again, the particles at the surface exhibit less attractive forces because there's nothing above them to be attracted to, so they're only attracted to the particles next to them and below them. And so that allows some of the particles to escape the liquid and become a gas. So let's say we have something like that. I'll try to kind of exaggerate it. So remember, those particles that are gases in the gaseous state are moving around, colliding with their surroundings, exerting something called pressure. So vapor pressure is the pressure exerted by a liquid's vapor. So when a liquid evaporates, the gas that is produced, the pressure exerted by that gas is called vapor pressure. So let's say, once again, we have some solute. Let's say it's water. But then we take, say, sugar and dissolve it in the water. So not only do we, I'm not showing anything here in the body of the liquid, I'm just showing the surface because that's where evaporation occurs. And so what happens is proportionally you have less solvent particles on the surface. So that's going to affect the number of particles that are able to change from a liquid to a gas. Not only that, but there are attractive forces between solute and solvent particles on the surface. And sometimes those attractive forces are pretty strong, once again, preventing some of the solvent from evaporating. So what happens is maybe you get something like this. Now remember, the solute is non-volatile, so it is not going to evaporate with the solvent. And so as we can see on the left, we have a lot more particles that are in the gaseous state here, which leads to a relatively high vapor pressure. In this diagram, we see there are less particles in the gaseous states because those solute particles are preventing some of them from evaporating. And this results then in a lower vapor pressure. So in summary, the vapor pressure of a solution is lower than the vapor pressure of the pure solvent. Now we can quantify that using this mathematical equation. So here's what it looks like. And I'll define these variables in just a second. And I had warned you about something a while ago that I will point out here once again. So P solution, SOLN, abbreviation for solution. P solution, that's a vapor pressure of the resulting solution. Greek letter chi here. Now remember we said you can calculate the mole fraction of solute or solvent. I think we did just solute in the last lesson, but here we want the mole fraction of the solvent. And then, of course, P solvent is the vapor pressure of the solvent by itself. Now let's think about this. What does mole fraction look like? If you have a mixture, what is the mole fraction of one of the components of that mixture? Well, mole fraction, the sum of the mole fractions in a mixture add up to 1. So the mole fraction of any one substance is going to be less than 1. So this is point something, 0.9, 0.8, 0.5, whatever the case may be. And so you have the vapor pressure of the solvent times some number that is less than 1. You're going to end up with the vapor pressure of the solution being less than the vapor pressure of the pure solvent. So something that's important also to reference is you have a table in your book on page 459. We've seen that before when we were doing Dalton's law and collecting gases over water. Water evaporates at a different rate at different temperatures, and thus the vapor pressure of water differs by temperature. So we may need that table to do some calculations. So 459 table 18.2. All right, speaking of which, let's take a look at some examples. It says find the vapor pressure of a water solution, an aqueous solution, in which the mole fraction of HgCl2, which is a non-volatile, non-ionizing. So I haven't mentioned this word yet. So non-volatile, doesn't evaporate, non-ionizing. We'll assume that this substance does not break apart into ions. If it does, then we have a different situation and we'll address that later. So mole fraction of the solute is 0.163 at 25 degrees Celsius. Use the vapor pressure of water in that table I referred to determine the vapor pressure of the solution. That's what we're trying to find. Find the vapor pressure of the solution. So let's start off with our equation here. So vapor pressure of solution is equal to mole fraction of solvents times the vapor pressure of the solvent by itself. All right, so if the mole fraction of the solute is 0.163, then what is the mole fraction of the solvent? So we're going to do 1.000 minus 0.163, and that'll give us the mole fraction of the solvent. Again, this is kind of like a percent. So 83.7% of all the particles in that liquid are solvent particles, 16.3% are solute particles. So again, just leave that as a decimal. If we go to page 459, we'll get the vapor pressure of water. So at 25 degrees Celsius, the vapor pressure of water is 3.2 kilopascals. Go ahead and pause the video, punch it up, and see what you get. All right, so water by itself has a vapor pressure of 3.2 kilopascals at 25 degrees Celsius. When you have this solution, the solution, of course, will have a lower vapor pressure than the solvent by itself. So we end up with 2 sig figs here. We'll go 2.7 kilopascals. All right, so go ahead and try this one on your own. It says ethylene glycol is commonly used in automobile antifreeze. If in a mixture of ethylene glycol and water, the mole fraction of ethylene glycol is 0.100, so keep in mind ethylene glycol is the solute. What is the vapor pressure of the water over the mixture at 100 degrees Celsius, which happens to be the normal boiling point of water? So let's see if you can do this without using the table on page 529. So we have water at 100 degrees Celsius. You should know the vapor pressure of water at 100 degrees Celsius. Go ahead and plug in your information, pause the video, and see what you get. All right, so of course, water at 100 degrees has a vapor pressure of 101.3 kilopascals. And so this solution then, of course, is going to have a vapor pressure of less than that. So dissolving a substance lowers the vapor pressure. This is important as we work towards thinking about boiling point of solution. So 91.2 kilopascals. All right, let's try one more, a little bit more complicated. Those other two were a little bit too easy. So we'll complex it up a little bit for you. This time we have 20 grams of sodium chloride, which is a non-volatile. Let's, just to make things a little bit easier for this calculation, let's assume that it is non-ionizing. So I said before, the solute ionizes. We have a little different approach to the problem. Just for simplicity's sake, let's say that this does not ionize. Let's pretend that's not true, but let's just pretend. So non-volatile, non-ionizing solute in 100 grams of water at 100 degrees Celsius. So we're going to apply Raoult's law. This time, though, we need to calculate the mole fraction of the water. This time we're given grams of solute and grams of solvent. And so we need to use those to find moles of each and then find the mole fraction of the solvent. I think I'm going to let you do this on your own. So go ahead and pause the video and calculate the vapor pressure of this solution now. All right, here's our setup. So I went ahead and just plugged in moles. You can calculate mole fraction separately if you want. So 5.56 moles of water over a total 5.90. So I just took those two and added them up to get our total number of moles. Multiply that by the vapor pressure of the solvent at that temperature, 100 degrees Celsius. And we end up with 95.5 kilopascals. So once again, we see that the vapor pressure of the solution is less than the vapor pressure of the pure solvent. All right, I believe that concludes our lesson for today. We have a lab coming up to see the relationship between boiling points of a solvent and boiling point of a solution. And we'll continue with that next time. All right, thanks for watching.